Hi everybody, my name is Lucas Sandre, and I'm an undergraduate student at the University of Toronto, Mississauga.
Hello, everyone. My name is Malaika Zaidi, and I just graduated from the University of Toronto, Mississauga, and this is joint work with Lisa Zhang. Today, we will be talking about our work on implementing a minimal relational floating point arithmetic.
So we implemented three basic relations: comparisons, addition and subtraction, and multiplication and division. Before we begin discussing our implementation, however, let's review floating point numbers. Floating point numbers are like scientific notation. If we want to write down the surface area of the Earth, we can do it like this. Here we are showing 5 significant digits, so we say that the precision is 5. There's one non-zero digit before the decimal point, so we call this number normalized. And the exponent is used to control the position of this decimal point. The same value can be written down in this format, and this is just to show that we're using a base 10 expansion. More generally, this is how we present a real number x in our floating point system. Here, beta, p, and L and U are characterizations of the floating point system. These represent the base, precision, and the allowed range of the exponent, respectively. Here, the di's are natural numbers, and the exponent range, L and U, are discrete values. More specifically, they are integers.
In our implementation, we use the following settings. The precision is a global constant that can be between 2 and 16. For simplicity, we use rounding by chopping and do not allow denormalized numbers. We represent a number in our system as a list with 3 elements and taking inspiration from the IEEE standard: a sign bit, an exponent, and a mantissa. Here, the exponent and mantissa are represented as a base 2 little endian representation of natural numbers. We actually use Oleg Kiselyov's Relational Natural Number Arithmetic library as helpers. Now, because the exponent is an Oleg number and you want an exponent to range from -126 to 127, we force the exponent to contain no more than 8 bits to get a range from 0 to 255. Then we shift it down by subtracting 127 to get the range -126 to 127. Finally, the mantissa is also an Oleg number. However, we fix the length of the mantissa to be equal to the precision of the system. Here are a couple more examples of floating point numbers in our system. Now we will begin the main portion of our talk with the introduction of our system's comparison relations. We implement 3 binary comparison relations. So the first one is FP equals, which is quite straightforward. The relation succeeds when the signs, exponents, and mantissa of F1 and F2 are equal, as can see here. Note, we also allow positive and negative zeros to be equal. Then we have the relation FP less than, and this relation can actually succeed in several ways, each corresponding to a Kondi branch. For example, one way for F1 to be smaller than F2 is for F1 to be 0 and F2 to be positive. Our next relation is FP less than or equal to, and this relation makes use of the previous 2 relations as discussed. Now Lucas will give you a quick demo of the less than or equal to comparison relation.
Here's an example that uses the FP less than or equal to relation. Here we perform a query that searches for 5 numbers which are greater than 1. And here's just the representation for 1 in the system, and we are using 8 bits of precision for this example. Let's run it. So as you can see, the query is resolved very quickly, and I'll just briefly go through the results. The first result is 1. That comes from the FP equality relation. The next result is infinity. This comes from the FP less than relation. Then results 4 and 5 are just in the interval from 1 to 2.
We're now going to move on to floating point addition and subtraction. Before we begin discussing our implementation, let's just review how floating point addition works. Let's take this example on the slide, which is in base 2 and the precision is 4. Our first step is to determine the smaller exponent, which is the second number. Then we need to rewrite that number by shifting the mantissa to match the larger exponent, like so. Now we just need to do simple addition by adding along the columns. And our last step is to truncate the result to ensure that precision is equal to 4, and hence this is our result. Lucas will be showing the implementation of the addition-subtraction relation, along with examples to show how the relation works.
Here is the code for FP plus O. The first thing we do is decompose our parameters, F1 and F2, our add-ins, and R, our sum, into their sign, exponent, and mantissa, respectively. Then we move on to separate it into two main cases, addition regarding 0 and infinity, and the more general case, which doesn't deal with 0 and infinity. In this case, we break it down into three main steps. Each step is done in its own relation. So FP plus O is responsible for rewriting the query so that all the addends and the sum have the same sign, either all positive and all negative. That's what this manipulation is happening right in these lines. Next, we'll move on to FP swap O. So here is FP swap O. FP swap O is responsible for ordering the exponents of the addends so that we treat the second parameter to have the largest exponent. This is an assumption that FP same sign adaro, our next relation that we're going to talk about, uses to actually do the addition. So that's what these two branches here. They just compute the difference of the exponents and then determine which one is larger. So then going down to FP same sign adaro, it follows the same steps as Malika just described, however, they are out of order, and this is for performance reasons, which was determined experimentally by running tests over and over again. So that was our implementation for FP plus O, and now I'll show you a quick demo. In this example, I have prepared two queries which use FP plus O. The first query will compute the sum of 4 plus pi, and then the second query will compute 4 subtract pi. Let's run the first example. Here we go. The query resolves really quickly, and we get the expected result. Because we're using 8 bits of precision, pi gets rounded down to 3.125. That's about it for this example. Now let's go on to subtraction. And subtraction is obtained by running FP plus O backwards. And here we go. As you can see, this query does take a little bit longer, but it's still resolved quickly. And another thing that's important to note here is that logic variables do appear in the mantissa. This is because you could assign those bits to either 0 or 1, and the relation will still hold.
Let's now move on to discuss floating point multiplication and division. But before we begin discussing our implementation, let's just review how floating point multiplication works. Let's take this example on the slide. It's a base 2 example where the precision is 3. So our first step is to determine the resulting sign by performing an XOR relation. So if two numbers that are being multiplied are positive, the product will also be positive. Then we need to multiply the two mantissas in a similar way to integer multiplication. Now we need to estimate the resulting exponent by adding the two exponents of the numbers. And now we need to normalize this number by ensuring that the decimal is placed after the leading 1. So the actual exponent will now be 3. Then we need to truncate the result to ensure that the precision is equal to 3, and this gives us our final result. Now, Lucas will be showing you our implementation.
Here is the code for FP multo. We first perform a decomposition on our three parameters, f1, f2, these are the multiplicand, and r the product. We decompose them into their sign, exponent, and mantissa respectively. We then branch into two main cases, a case to deal with special queries involving 0 and infinity, and the main driver for multiplication. This code follows the steps that Malika briefly just described. However, it is out of order. This is due for performance reasons. This ordering was determined experimentally by running tests over and over again. I will now show you a quick demo of using FP multo. Here is an example that we are prepared that will compute the product of 20 and 2, and it will compute the quotient of 20 divided by 2. Here is the representation for 2 and 20 in our system. Let's run it. As you can see, the query resolves quickly, and we get the expected result of 40. And 20 times 2 is 40. Moving on, we will now run FP multo backwards to perform division. This query will compute the division of 20 divided by 2. Not much else to say, let's run it. As you can see, this query also resolves very quickly, and we get the expected result of 10. 20 divided by 2 is 10. Let's explore how FP-Multo performs by squaring a couple numbers. The first number that we'll square is 0.001. Let's run it. As you can see, this query resolves very quickly. Let's just check out the next number, 0.05. This one's taking a bit longer. A lot longer. So this one took about 9.5 seconds to resolve. Right now you might be thinking that, 0.05 is larger than 0.001, so maybe FP-Multo is just slow with computing when working with larger numbers. Let's test this hypothesis by squaring 63. This one's fast again. So the hypothesis was wrong. What happens when we square an even larger number, like 32,888? It's taking longer again. So this one took about 3.5 seconds to resolve. Can you see the connection between these examples? It's the mantissa. Here you can see a plot of FP-Multo's performance against the number of non-leading ones in the mantissa. The fastest queries were 0.001 squared and 63 squared. These queries are fast because they have an easy mantissa for FP-Multo to work with. 0.001 has a small number of ones, and they're all evenly spread out. So that would correspond to this section in the graph right here. 63 has all of its ones located in the most significant range of the mantissa, and there is about 5 of them. So that corresponds to this section right here, where the purple line is still basically on the x-axis in this graph. The slowest queries were 0.05 squared and 32,888 squared. 0.05 squared is slow because of the number of ones. If you paid attention, there was 7 ones in the mantissa, and they were evenly spread out. So that would correspond to about this section in the graph right here, and the data point would be right about here. 32,888 is slow because there are 4 ones concentrated on the least significant side of the mantissa, so that corresponds to this part in the blue, on the blue line right here, right as it starts to hit that exponential ramp up. So you can see that there's this exponential behavior when it comes to the number and the position of the ones in the mantissa. For our last section, we'll be discussing an interesting example. We will be exploring quadratic equations which determine the golden ratio. We will run these equations using precision values 5, 6, and 7 and observe the behavior. Let's get right into it. So here we are, where we've created a couple queries. Here is the first query. This is x squared is equal to x plus 1. Here we set y to be equal to x squared and equate it in FP plus O. Notice that there's this extra finite relation. This is because there's a variable on the left-hand side and the right-hand side of the equality sign. So if we substituted infinity for x, we would get infinity plus 1, which is equal to infinity, is equal to infinity squared, which is true because positive infinity squared is positive infinity. Moving on to the second form, we have x times x minus 1 is equal to 1. Here, I'm just performing a relational trick so that I don't have to define -1. And let's run it. Let's get the first value out. So, as you can see, these queries resolve relatively quickly. The first query, x squared is equal to x plus 1, took 2 seconds, while x times x minus 1 only took less than 1/5 of a second. Let's run it with precision value 6. So you might expect that these will take longer, which is the case. There is this exponential behavior when you increase the precision of the system. So here you can see that the x squared equals x plus 1 query took about twice as long as before, and the x times x minus 1 query took 1.5 seconds this time. Can anybody guess what happens when we bump up the precision to 7? Let's check it out. So, as you may expect, these queries will take longer. So we're just going to have to give this a minute. Not a whole minute. So, we actually won't wait for this next one to terminate, and that's because when the precision value is 7, there is no solution to x times x minus 1 equals 1. So this query would end up having to exhaust the entire search space to find that, so we're not going to wait for that. The reason why this doesn't have a solution is so any number that would be close to a solution, let's say x, if we multiply it by x minus 1, we won't get exactly 1. We'll get 1 with a couple bits set to 1 at the end of the mantissa, the least significant end of the mantissa, and this causes the results to be thrown out. Overall, we've just observed that even though that you are searching for the same value using equivalent equations, you can get varying behavior amongst the queries.
So to conclude, I wanted to talk about some learning points we had while working on this project. First, we found that ordering the conjects was not trivial. We tried many different orders, and it was just hard to predict what would and wouldn't work. Next, debugging was challenging. It's hard to tell why a relation is slow and what part is slow. We didn't know about G-display for a long time, and using it wasn't intuitive. Debugging relations in general is much harder than debugging functions. We also tried to drop the leading one to be consistent with the IEEE standard, but then quickly realized that it made things way too slow. We also wanted to support denormalized numbers, but it requires the mantissa to have a change in length, which ends up increasing the search space. Thank you for your time.
We hope you learned a lot about floating point arithmetic and enjoyed our talk.